the relationship with exponential, which again it will be taught when Deboshida or me will teach in the next week. So, one second. Let's try to prove it's gamma. Okay, let's try to prove it's gamma. So, what we're trying to understand, time taken for the first R successes, right? This is a random variable G. Let's call it random variable G. G is the time taken to get to the first RH success. How to show it will be a gamma? You have to find the PDF or the CDF, any one of them. Let's try to find the PDF, okay? Because the CDF is hard to find. The time taken for the first RH success. So, FG of this. So, how will you do this? Let's see. So, therefore, let's understand this very carefully. Okay, so let's do this thing. Let's try to take the first time taken to the first success, because we will show that sum of exponential is gamma in the next classes. So let's take time taken for the first success or for the first arrival. Okay, let's call it E. Let's call it E. So we're going to find f of E of, or f of, or let's call it X. Let's find the distributor, the PDF of X. Okay, or the CDF. Let's see what we can find out. So understand it very carefully. So what we'll do is that, so if you remember, we have proved something. In fact, memoryless property, if and only if it was geometric. Similarly, memoryless property, if and only if it's exponential, we can prove that by a similar approach. But let's try to find it. The time taken for the first, let's try to find probability X less than equal to X. That is, time taken for the first success is less than equal to X. Now understand, you know that the NT, the number of successes till time t, follows Poincare lambda t. You know this, okay? Let's try to apply it here. The time taken for the first success is less than equal to X. That means what? That means one success has occurred. Only one success occurred in 0 to X interval time, right? Only one. Did you understand this, all of you? Did you understand this, all of you? Great. So therefore, probability. I missed the probability word. Therefore, its probability NT is 1. NT is 1, right? Or did I miss something? Only one success occurred in time t is less than equal to X. Yes. Now, what is the probability NT is equal to 1? So let's not think like this. Let's think greater than X. Let's think the other way around, okay? Let's think the other way around. So the issue is that, the problem is that once here in this argument, one success can also happen in a less than X time, right? There's an issue. So what if we say 1 minus probability X less than X? That means 1 minus probability that, what is X less than X? The time taken for the first arrival is more than X. That means no success happens in 0 to X, right? This is much more interest. This is much more better. That 1 minus probability that X greater than X means no success has surely happened in 0 to X. So therefore, it's 1 minus, what is probability? That means the n of X, the number of successes that happen till time X, is nothing but 0. Now this n of X is nothing but what Poincare. Therefore, Poincare lambda X is equal to 0. Now Poincare lambda X is equal to 0 means what? E to the power minus lambda X, e to the power minus lambda, lambda to the power K by K. K is 0 here, so e to the power minus lambda X. Therefore, the CDF of X is nothing but 1 minus e to the power minus lambda X. Therefore, the PDF will be lambda to the power e to the power minus lambda X. So what is this? This is nothing but X follows exponential lambda. It's super, it's easy, it's beautiful actually. So it shows you the connection between counting, and this is very beautiful, okay? This, I find this very beautiful, this connection, okay? I really like it. So for time times the first success follows. If you remember, I told you that Poincare can be used to, estimate small probability events for a long time, long number of trials. So the example is this. The continuous time is nothing but small interval for a long time, long number of times. Hence, continuous random variables, counting process in continuous state setup. In continuous time, counting processes are usually done by Poincare. So you will see this, if you read a lot of papers, if you do a lot of real life work, you will see counting processes in continuous time is done by Poincare process. It's Poincare distribution. That's the idea of Poincare. That was when that was how Poincare distribution came into existence. Yeah. Did the answer get clear?
Yes.
Any other questions? So similarly, the inter-arrival time will be again exponential, and we will show how gamma and exponential are related by MGF, sum of MGF stuff. So you have got all the arsenals in your arsenal, like all the instruments in the arsenal, how to deal. Sum ke liye MGF is there, and you have understood all these things. So just practice and practice more now. Okay. So therefore, this shows you the connection between the random, the continuous, and the discrete setup. Okay. And this is very, 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 very important to make. It's not in the syllabus, but it makes your understanding so concrete that if a random problem is given, you will understand and see through it. Okay. Very easily. And that will be a superpower, getting into IIT ISI after, learning from us. I don't think it's, I know great people who didn't get from here, okay? But I want you to, when you get out of Cheenta, I want you to be such a person who can see things through, okay? So who can read between the lines, I should say. That intuition, that extra tinge is what makes you the difference between a ranker and a person who is knowledgeable and also a ranker, okay? Like it gives a distinction between 3 days Chaturanga Ramalingan and Rancho. Okay, if you understand that tinge of reading between the lines, because it only happens when you try to understand into the depth of it. So that is what we preach and teach over here in Cheenta. Okay, and that's what we want you to continue as your legacy in your work, whatever you do, in whatever form you do. Okay, and you should always strive for that. Okay. So, so whenever people come to us to enroll in our courses, we right away tell don't express formulas and all these things from us. Of course, that is important for the examination. We'll do that when it's required, not all throughout. It's kind of sick if you do all throughout. So yeah, so it's okay. So you should stop sometime and see the beautiful aspects and the connections between. Okay, it's very important for your growth and understanding and knowledge. So all of you confident in this, all of you can see through the connections between continuous and discrete random variable.